Hi, today I will talk about the reduction types of absolutely simple Abelian threefolds with complex multiplication. First, let us start with the motivation of classical reduction theorem. Let E be an elliptic curve defined over a number field M. Let the endomorphism ring be isomorphic to OK, where K is an imaginary quadratic field. Let P be a prime of good reduction for E. Let FQ be this quotient. Let EP be the reduction mod P. Then the cardinality of the P torsion points is equal to this number, and we say the power is the P rank. In this setup, we have two cases. If the E is ordinary, then the endomorphism algebra is isomorphic to K. Then P rank is equal to 1, and P splits in K. In the second case, E is supersingular. The endomorphism algebra is isomorphic to quaternion algebra ramified at P and infinity. And in this case, P rank is 0, and P is ramified or inert. And we don't have such equivalence relations in higher dimensions. Okay, so let us generalize that. Let A be an Abelian variety defined over a number field M of dimension G. Suppose the endomorphism ring is isomorphic to OK, where K is again a CM field of degree 2G. A has CM by a primitive CM type phi. P again a prime of good reduction for A, and FQ as in above. We will denote AP as the reduction mod P. The P rank of AP is the rank of the P torsion points. So we have questions. In dimension 3, can we read the P rank of AP and the endomorphism algebra from the decomposition of P in K? It's no, but we can read it from the decomposition of P in K and the decomposition of the Frobenius endomorphism pi in Q pi. So what is known? In dimension 2, Goren and Lauter gives a full classification for every type of prime decomposition, and in dimension 3, Zaitsev computes to P rank and A number only for unramified prime decompositions. Our aim is giving a full classification for P rank, A number, and endomorphism algebra in dimension 3 for every Galois type, which must be of this type, for every decomposition type, and for every CM type. Okay, so in order to understand the geometry of this Abelian variety, we will look at the structure of endomorphism algebra. So we are understanding the geometric object by looking at an arithmetic object. So there's a famous theorem by Tate. Let A be a simple Abelian variety of dimension G. Then we have this equation, which is a general theorem for any dimension. If we take K as a CM field of degree 6, A is absolutely simple Abelian variety of dimension 3 over M and has CM by OK. P is a good reduction, and AP as in before. Then we have this theorem. AP must be isogenous to B to the S over FQ bar for S 1 or 3. In case S equals 3, B must be an elliptic curve. Then by Tate, we have this equation. Okay, so our setup as before. Then we have 4 cases for this Abelian variety. The first is AP is absolutely simple, and the morphism algebra is isomorphic to K, and the characteristic polynomial of the Frobenius endomorphism is irreducible. Or AP is absolutely simple, endomorphism algebra is central simple division algebra over the imaginary quadratic field Q pi A, and this FA is equal to H cube. We will come to H later. Or AP is isogenous to E to the 3, where E is an ordinary elliptic curve with CM by the imaginary quadratic field Q pi E. Or AP is isogenous to E to the 3, where E is a supersingular elliptic curve with endomorphism algebra isomorphic to quaternion algebra ramified at P and infinity. This is a very important proposition to understand AP. We will classify our cases up to this. Okay. We have invariance. As before, we have this equation. this index is equal to the least common denominator of the invariants, which are those. Okay. For primes not dividing the ideal pi a in Q pi a, we have IP congruent to 0 mod 1. One needs to know the prime decomposition of pi a in Q pi a in order to understand the structure of endomorphism algebra. So, okay. Prime decomposition of pi a in Q pi a, another famous theorem by Shimura and Taniyama. In this case, we see directly the prime decomposition of pi a in terms of the type norm and the ideal norm. As a remark, by a theorem of Serre and Tate, it basically says that if you take M big enough, every prime will be a good reduction, which is important. Okay, let us look at the example. Let K be a sextic CM field not containing the third root of unity. Let L be a Galois closure of K with Galois group D20. Let phi equals, let us take the type as this. Then the reflex field KR is equal to K, and the reflex CM type phi R is phi. Let us take our inertia group as you've seen before, actually, in here. And composition group as y square. Then POK equals to PK1 times PKY, and our residue degree is 3. This was the one that we seen in Shimura and Taniyama, which is equal to this, and it's equal to this. And pi times pi conjugate is equal to pi to the 3. And we have this. Okay. The ideal POK is not fixed by y, so I don't know. You shouldn't count it, right? Okay, the ideal POK is not fixed by y, so Q pi is not equal to Q. The ideal POK is fixed by y square. Therefore, we have y square pi equals to pi u, where u is actually unit. In our case, u must be a root of unity. Since k is a dihedral extension, u is contained in the imaginary quadratic subfield k of big K. Then we get this. Therefore, u must be a power of the third root of unity. This contradicts with the assumption if e is not equal to 0. So we get y square u equals u. Hence, k is this. Okay, let us compute the invariance. We have POK equals to PK times PK conjugate, and POK equals to PK times PK conjugate to square. In this case, IPK is 1/3, and IP bar K is 2/3. And by Tate, we've seen before, this index is equal to 3. This is actually one of the hardest examples that we find, or the most interesting one. Therefore, the endomorphism algebra is a central simple division algebra of degree 9 over the imaginary quadratic field Q pi A. The reduced variety AP is absolutely simple. Okay, so let us come back to the cases. As you've seen here, these were the cases. So we will just consider on that. Okay, let us start with case 2. Let us look at for the P rank. AP is absolutely simple. The characteristic polynomial of the Frobenius endomorphism is equal to h cubed, where h is a second degree irreducible Weyl polynomial. There's a general theorem by Honda which says this. By that, we conclude that the P rank must be 0. In the previous example we saw, we found that AP is simple and the Frobenius element generates imaginary quadratic field. Therefore, we are in this case, so we get P rank is 0. Okay, in case 3 and 4, that was the conditions. So if E is ordinary, we get the P rank is 3, or If A is super singular, we get P rank as 0. Okay, in case 1 is the most interesting one. AP is absolutely simple. The endomorphism algebra is isomorphic to K, and characteristic polynomial is irreducible. Then, by these equations, we find that K is equal to Q pi. We can compute, then by this, we can compute the prime factorization of P OK and pi A OK by, yeah, we can compute the prime factorization, then our P rank is equal to that sum. Okay. In cyclic case, we make this table. We are choosing I's and D such that, let me write quickly. Let me write here. We are looking at each cases such that I is normal in D and D over I is cyclic. Okay. And in this case, D is a subgroup of, in cyclic case, Z over 6n. After that, we will also look at D2. Okay. Okay, in this case, in this table, AP has Cm by K only in case 1, which is this. AP is not isogenous to product of ordinary elliptic curves. The only possible ranks are 0 and 3 there. Okay, in the other case, it will be different. Okay. So we are assuming that the third root of unity is not in K. After that, we will, in the future, we will generalize that by finding an argument which is not assuming this. Okay, so this is our case. We see in this case we see different P ranks as you see in here. Okay. There is more. We compute all these things. Okay. So what's next? Next, do P rank endomorphism algebra depend on choice of the primitive CM type, computing the A number from the prime decomposition of P and pi, make tables for the Galois groups of these groups. These are more horrible than the others, and explicit examples, giving explicit examples. Thank you.